Welcome to the second lecture of Module 7. We're going to be using operator methods to calculate spherical harmonics, and in so doing, we're going to be showing you the power of operators. So today we're going to be talking about spherical harmonics. Spherical harmonics are the coordinate space wave functions of the angular momentum eigenstates. And so we're going to be using the simultaneous eigenstates of the square of angular momentum and the z component of angular momentum. And those are the states L comma M that we were working with in the previous lecture. We're also going to use the angular coordinates in position space given by the states theta comma phi. These are the states that you worked with in the classwork during the last class session. Now, we worked on determining all of the properties of the angular momentum eigenstates in the first lecture. And we were able to verify all the algebra and all the other relevant properties. We're going to describe some of the properties of the angular coordinate states in just a bit as the next thing that we do in this lecture. But before we leave this page, we want to define exactly what the spherical harmonics are, because they're the wave function given by the overlap of the spatial bra given by theta phi and the ket given by Lm. And these functions are denoted y sub Lm of theta phi. And those are very time-honored old functions. They were known way before quantum mechanics, and it's really quite surprising that they come out in exactly the same fashion in quantum mechanics as they did in classical mechanics. All right, so let's talk about these angular coordinate states. I want to just remind you that there are no operators that correspond to angles in quantum mechanics. The situation is similar to the situation we had for the coordinate when we solved the problem of the particle on a circle. We worked that out in Module 6, and there we found that the position operator was not a good operator, but cosine of 2 pi x hat over L and sine of 2 pi x hat over L, those both were well defined because they had the same periodicity as the length of the circle or perimeter of the circle, which was L. And so those objects were well defined. And this was because we were picking periodic boundary conditions on the circle. Now, in an angular space, if I'm using angular coordinates, we have the same kind of periodicity properties as we would have as we go around from 0 to 2 pi, but you do have to be a little bit careful. There is no requirement that the wave functions themselves are periodic, and indeed we have to use other arguments to get to determine the fact that the angular momentum is made out of integers when it's an orbital angular momentum written as r cross p. You're going to have more about that on a homework. I'm not going to talk about that any further. But the same thing is happening here where the length L is equal to 2 pi for the angles. And so what we find is cosine of theta hat and sine of theta hat are going to be good operators that we can use, but the angle operators themselves, theta hat and phi hat, they're not well defined. So what is particularly interesting is if we define the radial coordinate by r squared equals rx squared plus ry squared plus rz squared, and then the angular coordinates can be defined entirely in terms of the Cartesian position operators. We're going to have to take a square root, and taking the square root of an operator is something that is rather natural. The square root operator has the same eigenfunctions as the operator. It just has eigenvalues that are given by the square root of what the eigenvalues were for the squared operator. All right, so we're going to define the radius or radial coordinate by the square root of rx squared plus ry squared plus rz squared, all operators. And we're going to define the polar radius, rho hat, by the square root of rx squared plus ry squared. And then if you just go and look into how we represent x, y, and z in spherical coordinates, you can very quickly verify that cosine theta will be rz hat over r hat, sine theta hat will be rho hat over r hat, cosine phi hat will be rx hat over rho hat, and sine phi hat will be ry hat over rho hat. And now you might think, well, how do I actually use these definitions? Well, the way to think of it is, again, theta hat and phi hat are not well-defined operators, so we don't work in terms of theta hat and phi hat, but I can very easily work in terms of cos theta hat because I can just write that as rx hat over r hat. And similarly, cos phi hat is rx hat over rho hat. And so because those operators are just constructed out of the Cartesians, they're very easy to work out and determine what the angles are. The only time I run into trouble is if I'm at the origin, because at the origin things become ill-defined. But in this case, what we find is no angles are well-defined at the origin, and the radial coordinate equal to 0 is all that we need to define and work with states. And so even though they're not well-defined when we're at the origin, it actually doesn't cause any problems with the way in which we're going to work with these operators. All right, so the angular states are eigenvectors of these operators, the cosines and sines, not the operators themselves. And so cosine theta hat acting on theta phi is cosine theta times theta phi, and similarly with the sine theta hat and the cosine phi hat and the sine phi hat. And so there are nice eigenvalue, eigenvector relationships for these different operators, but it's not exactly in the same form as what we've seen before when we're looking at eigenvalue, eigenvector relationships. And, as I'd mentioned before, we can represent all of these equations in terms of the Cartesian operators. And so we really know how to work with these if we want to. All right, so we also showed that we can determine these states from the North Pole state by two rotations. Now, remember, the North Pole state points along the positive z-axis, and we denote the North Pole state by 0 sub theta and 0 sub phi, even though the phi value is actually arbitrary there. This ends up streamlining some of the equations that we're using, but if you want to be a purist, you could say that it's arbitrary when we are at the North Pole. But once we rotate off the North Pole, the value of theta phi is very important, and in the procedure that we're using to rotate off of the North Pole, it will be 0 once we do that rotation. And so that's another reason why picking it to be 0 is a reasonable thing to do in the equations that we're going to be writing down. Now, we constructed the state at theta phi from the North Pole state by applying two rotations. We rotated by theta about the y-axis, followed by a rotation by phi about the z-axis. And now if you remember how states are modified due to a rotation, you can see that the state theta phi is simply written as e to the minus I over h bar phi Lz hat. That's the second rotation. E to the minus I over h bar theta Ly hat. That's the first rotation, acting on the North Pole state. And if I take the ket, I have to take complex conjugates of those operators. Ly and Lz are Hermitian operators, and so theta phi bra is equal to 0 theta 0 phi, or the North Pole state, e to the I over h bar theta Ly hat, e to the I over h bar phi Lz hat. And you see the order switches because when we take the Hermitian conjugate of products of operators, the order switches, and I've changed the minus I into a plus I because I need to take the complex conjugate. All right, we're now ready to start working on constructing the spherical harmonics. And so they're simply written in this form. I take the overlap of the rotated state at theta phi with the angular momentum state Lm. I rewrite that in terms of the North Pole state with the operators. And now if you look at the first operator, the one acting to the right on the Lm state, the state Lm is an eigenstate of Lz. And so we can immediately figure out what happens when that operator acts on the state Lm. It's going to just give me an e to the I m phi. And so I can just pull that operator out and boom, I'm done with that operator. Now I'm still left with another operator here. And what we're going to do first is we're going to introduce a complete set of states in terms of the angular momentum states. If I sum over L prime and M prime, that does satisfy the completeness relation. So that's the same as multiplying by 1. I'm now going to recognize that because Lm is an eigenstate of the total angular momentum, L squared, I can multiply that state Lm by L squared divided by h bar squared L times L plus 1. At the moment, let's not worry about the fact that that won't work for the S-wave states where L is equal to 0. There's a simple modification of this argument you can use for that case. Now, because L squared commutes with Ly, I can just move that L squared to the other side. And then that L squared is going to give me h bar squared L prime times L prime plus 1. And if I divide that by the h bar squared L times L plus 1, I'm going to get L prime plus 1 over L times L plus 1. But that has to equal 1 because I didn't change the operator at all. I just multiplied and divided by an eigenvalue, and I evaluated that eigenvalue by operating to the left or operating to the right. It can't change anything. And so what that tells you is that that thing is non-zero only if L is equal to L prime. So we can get rid of the sum over L prime and replace the L prime by an L. And now I can pull the summation out. And what you see, I have two factors. The first factor is actually just a number. It's the overlap of the North Pole state with the state Lm prime. And the state on the other side is something that we call a rotation matrix. So this matrix element, or this matrix, if I think of M and M prime, we denote it d sub M prime M of L of theta. That's called the rotation matrix. It turns out we're going to only need the M prime equals 0 column of this matrix. And the reason why is because the North Pole state is invariant under rotations about the z-axis. So if I take the state 0 theta phi, which I can think of as taking the North Pole state and multiplying e to the I over h bar phi Lz hat on it, we know that that has to be the same as the North Pole state because I could pick an arbitrary value for the phi rotation. Now, if we evaluate that with an inner product with the Lm state, I can operate that operator to the right against the Lm state, and I get e to the I m phi. But you can see that the North Pole state overlapped with Lm must equal the North Pole state times e to the I over h bar phi Lz multiplying Lm. And in the second case, I get this extra factor of e to the I m phi. But it can't change anything. It has to be the same number. And that will only occur when m is equal to 0. And so that overlap of the North Pole state with the state Lm is 0 unless m is equal to 0. And by the way, because we have m equals 0 in our angular momentum states, that's actually an alternative proof to show that angular momentum must be an integer, because it tells me that the m's are integers, but we know the maximal m is when m is equal to L, so that then tells me L is an integer as well. And so this is an alternative proof, the invariance of the North Pole state being evaluated against the Lm eigenstates gives me an alternative proof that the angular momentum is an integer. All right, so the matrix element is 0 unless m is equal to 0, as we just concluded a little bit earlier. All right, so I can replace that with a 0. I get rid of the sum, and now we have this matrix element that we have to evaluate. The first term is just a number. That's going to end up being the normalization constant. We're going to determine that at the end. And the second one is this matrix element that we need to calculate. So let's think about what are some strategies that we can use to calculate this. Well, one thing you might think of is, look, that there's an Ly up there. I can rewrite the Ly in terms of the raising and lowering operators, and then I can separate out the raising and lowering operators to the left and the right, do something like a BCH on it. But we find if we try to do that, we'll get a commutator of L plus with Ly, and that's Lz. And then I'll get a nested commutator of L plus or L minus with Lz, and so forth. And it just keeps going on forever. It never ends, and since we don't know the coefficients of all the terms, we'll never be able to recognize a pattern. It's not a simple expression like the Hadamard lemma. The BCH is this very complicated expression, and so trying to do this with BCH just doesn't lead you anywhere. So what can we do? Well, remember, we have our third fundamental operator identity. That's the, or maybe it's the second, I think it was the second fundamental operator identity, the exponential disentangling identity. And that is the one that we can use here. So remember, we only have a handful of fundamental operator identities. If one doesn't work, let's look at another one. Exponential disentangling is the thing that comes to the rescue. So what we're going to do is we're going to take that e to the I over h bar theta L hat y. We're going to rewrite it in terms of L plus and L minus. It becomes e to the theta over 2 h bar L plus minus L minus. We then use exponential disentangling. I'm not having you go look it up. I'm just telling you what it is. It becomes e to the minus tan theta over 2 L minus over h bar, e to the log cosine squared theta over 2 Lz over h bar, and e to the tan theta over 2 L plus over h bar. And so that's an operator identity. I just substitute that in for the operator. And now let's think about what is happening in this expression. So the exponential of an L plus, that has to be a finite polynomial. Because when L plus acts on Lm, I can only let it act a number of times before I get to L plus acting on L comma L, and that equals 0. And so if I expand that exponential in a power series, only the terms through L minus m in the power are going to be present, because all of the rest have to be 0, because if I try to raise past m equals L, I get 0. And then the next operator depends on Lz, but every one of these states is an eigenstate of Lz, so I can immediately evaluate that exponential acting on the state Lm. And then the final state is L minus, and that also can have just a finite number of terms, but it's even better than that, because remember, we have to end with the state L comma 0, because these states, these angular momentum eigenstates, are orthonormal. And so I only have to worry about the term in the exponential that reduces the state that I'm at down to L comma 0, and then I'm done. Okay? So let's go ahead and calculate this step by step. We're going to assume that m is greater than or equal to 0, because in that case, it just makes the bookkeeping a little bit easier, and there's a very simple relationship that relates m greater than 0 to m less than 0. So we don't have to worry about that. So we can just make our lives easier by assuming m is greater than or equal to 0. All right, we also have to recall what happens when L plus acts on an Lm state. We worked out the exact number that happens with that. It's square root of L minus m times L plus m plus 1, and it raises from Lm to Lm plus 1. Okay, so now what happens? We take that power series for the exponential, sum n equals 0 to infinity, 1 over n factorial, tangent theta over 2, raised to the nth power, L plus over h bar to the nth power. Now we just evaluate those L pluses acting on L comma m. Remember, we did something very similar to this when we were working on the explicit formula for the eigenfunctions in terms of the lowest weight state. And so now we can evaluate what happens when we operate this term on it. We're going to get a product of these factors, L minus m, L plus m plus 1. But remember, the m is going to be increasing. The first case, it's m. The next case, it's m plus 1. The next case, it's m plus 2. The next case, it's m plus 3. So generically, I'll write it as m plus r. And I'll take the product of those square roots running from r equals 1 all the way out to n. And I'll have a state that is L comma m plus n, because I acted on this n times. And of course, if m plus n is bigger than L, then the whole thing is equal to 0. And so I don't need to keep my bookkeeping anymore. And so what that means is I can replace that sum as a sum that goes from n equals 0 to L minus m. I get the 1 over n factorial. I get the tangent theta over 2 raised to the nth power. I get this product of all the square roots. And now I'm ready to evaluate the next term. So I'm going to bring that in. That's the exponential of the logarithm of cosine squared theta over 2 times Lz over h bar. It's just an eigenstate, so the Lz over h bar just gets replaced by m plus n. So I'm going to just replace that. And now an exponential of a logarithm just becomes the argument of the logarithm. So this is going to just become cosine squared raised to the m plus n power, or cosine raised to the 2m plus m n power. And so I write that as cosine theta over 2 to the 2m plus 2n. I still have this product of numbers that I have to worry about. And now we're going to bring in our last factor. The last factor is this exponential of the tangent with an L minus. I'm also bringing in the bra, which is the L comma 0. That bra tells me that I have to look at the power that is the m plus nth power in that exponential. Only that term will contribute. And when that term contributes, it's going to lower the L comma m plus n state down to L comma 0. And I'm going to get a product of factors very similar to this product. You just carefully work out what those factors are using what happens when L minus acts on the state. And then we also remember that L comma 0 overlap with L comma 0 is equal to 1, because all these eigenstates are orthonormal. Okay, so I get the second product coming out, And the bra with the ket is going to give me 1. And now you can see I have a tangent, I have a cosine, I have a tangent. Let's group those tangent terms together. I'm going to pull out a factor of -1 to the m plus n, and I'm going to get tangent to the m plus 2n. So what I'm going to do is I'm going to take a cosine squared raised to the mth power and multiply it by tan theta raised to the mth power. And then I'm going to get a sine theta over 2 cosine theta over 2 to the mth power. That's equal to sine theta divided by 2 raised to the mth power. And I'm still left over with a tangent theta over 2 to the 2nth power times a cosine theta over 2 to the 2nth power. I multiply those two together, I'll get a sine theta over 2 to the 2n power, or sine squared theta over 2 to the nth power. And so you see I'm going to get sine theta raised to the mth power and sine squared theta over 2 raised to the nth power. And now I'm going to rewrite sine squared theta over 2 as 1 minus cosine theta divided by 2. So I'm going to get another factor of 1 over 2 raised to the nth power. And so my numerical factors become -1/2 raised to the m plus nth power. I still have the n factorial and the m plus n factorial. I have the sine theta raised to the nth power and a 1 minus cosine theta raised to the nth power. And then I have the product of all these constants. So let's go ahead and work on the product of all those constants. We can rewrite those constants. Let's go back and take a quick look at them. You see I'm going to have a product of L minus M minus R plus 1. When R is equal to 1, that's L minus M. When R is equal to N, that's L minus M minus N plus 1. And so you can see that's going to be a product of L minus M factorial divided by L minus M minus N factorial. And then if you look at the L plus M plus R, that's going to be L plus M plus 1 multiplied all the way out to M plus N. That's going to be M plus N factorial divided by L plus M plus N factorial divided by L plus M factorial. And then you do a similar thing with the right-hand side. You just need to sit down carefully and look at it. If you're having some trouble with this, it might be a good time to pause the video and carefully go through it. But I'm going to just show you what the answer is in terms of these square roots. You can see there we have that L minus M factorial divided by L minus M minus N factorial, like I told you. And then we also have the L plus M plus N factorial divided by the L plus M factorial, just like I said. And then from the second term, you get an L plus M plus N factorial times an L factorial divided by an L factorial times an L minus M minus N factorial. Now we can do some cancellations. The L factorials cancel. The L plus M plus N factorial terms, those become squared. The L minus M minus N factorial terms, they become squared. I can pull them out of the square root. I'm left with an L minus M factorial over an L plus M factorial inside the square root. So we get L plus M plus N factorial, L minus M minus N factorial, and the square root of L minus M factorial over L plus M factorial. Okay, look, it's starting to get kind of messy, but really this is a French cooking problem. Each step is relatively easy. You just got to stay with me for the long haul and get through it all. We're getting very close to the end. Okay, now we're basically, what we're doing here is we're going to pull out all of the terms that don't depend on n. So you see I have a sine theta to the nth power. I have a -1/2 to the nth power. This square root of L minus M factorial, L plus M factorial, that doesn't depend on n. So I'm going to pull all those factors out. And of course, we still have that normalization constant and the e to the I m phi that we had before we started working on this matrix element. And I have this sum n equals 0 to L minus M of this messy thing. I'm not going to read it out for you again. And basically, we're now done. Okay? Except it is tradition to re-express calculations you've done in quantum mechanics in terms of things that dead German and French mathematicians have already done before you. And so which dead French or German mathematician do we have this time? It's Adrien Marie Legendre. And it's a very interesting story about this. That's an absolutely horrible looking picture of him, but it's the only existing picture that is around. There apparently was a Legendre who was a French nobleman, and everyone thought that his portrait was the mathematician, but it turns out someone did some research, figured out it wasn't. So that picture that everyone used to have of Legendre was the wrong picture, but people have actually verified that this is a correct portrait of Legendre. It looks like it's an unfinished portrait. He doesn't look like a very happy guy, unless this was a caricature, but in any case, that's all we have for him. And so we're going to be now looking at what he did. he constructed something called associated Legendre polynomials, and they're given by P sub L sup m of cosine theta is equal to sine theta over 2 raised to the nth power, sum n equals 0 to L minus m minus 1 to the n, L plus m minus n factorial over L minus n factorial, m plus n factorial, 1 minus cosine theta over 2 raised to the nth power. Now let's look at that summation that we have above. If you look at it carefully, you can match term for term. I'm going to have to borrow a sine theta over m divided by 2 to the m, and then I get this Legendre polynomial, and everything that's left, those are extra coefficients. So let's go ahead and do that. We can then rewrite the YLM of theta phi in terms of normalization constant, e to the im phi minus 1 to the m, this square root factor, and then the associated Legendre polynomial. Okay? Now we have just one step left. We have to do the normalization. I also should just tell you that in the case when m is less than 0, there's an identity that you can work out that YL comma minus m of theta phi is minus 1 raised to the absolute value of mth power YLM of theta phi complex conjugate. And so with that, we get all of the negative m values from the positive m values that we have the explicit formula for above. All right, normalization constant, we still have to get this, and it turns out it's easiest to do this for the case where m is equal to L. So we go and we evaluate that associated Legendre polynomial when m is equal to L. It's just equal to sine theta raised to the Lth power divided by 2 to the L times 2L factorial over L factorial. So it's relatively simple. And now we evaluate what that is. We plug that in to get the spherical harmonic, YLL of theta phi. We take the absolute value modulus squared of that and integrate it over the spherical angles, the theta and phi integrals over the surface of a sphere. And so what we get is 1, because it has to equal 1, and I'm looking at the absolute value modulus squared of this. You can see I'm going to get a sine theta to the 2L power, but the integration measure has a sine theta in it. So it becomes sine theta to the 2L plus 1. I'm integrating from 0 to d theta. I'm going to have 2L factorial, 2 to the 2L divided by L factorial squared, an integral from 0 to 2 pi, and then I have the modulus squared of the normalization constant. Now the integral from 0 to 2 pi of d phi, that's just equal to 2 pi. You can see that I can pull the constants out, and I just am left with this integral from 0 to pi d theta of sine theta 2 to the L plus 1. You can just look up what the answer is for that. If you wanted to, you could write this as an integral d cosine theta, but then the sine theta would end up being a 1 minus cosine squared theta raised to the Lth power. You'd have to use the binomial theorem to work that out and so forth. It's a little bit of a pain. But you can also just look up in a table, go to Wolfram alpha, whatever you want. You can get what this integral is. It's equal to 2 to the 2L plus 1, L factorial squared over 2L plus 1 factorial. You can see we got a lot of cancellations. So the 4 to the L cancels with the 2 to the 2L. I'm left with one factor of 2 that combines with the 2 pi to give me 4 pi. The 2L factorial cancels with the 2L plus 1 factorial, leaving behind a factor of 1 over 2L plus 1. And then the L factorial squared cancels upstairs and downstairs. And we're just left with 4 pi over 2L plus 1. I have to take the square root of that. That's going to equal my normalization constant. So I get the normalization constant as square root of 2L plus 1 over 4 pi. And now we just go ahead and plug that into our formula. And we've gotten now the final spherical harmonic. And that's it. We're done. We've done everything for that. For m less than 0, of course, we do the thing that we said. We multiply possibly by a factor of -1, and we take a complex conjugate. And I just want to remind you a couple of things. So first off, these results are very important. You don't need to memorize them because they're kind of complicated. But you do need to be familiar with them, and you need to be able to work with them if you're given a specific value of L and M to work with. We're going to be doing that during the class time. Again, I hope you see how incredibly powerful these operator methods are that we're working with. Everything that we did here, we built upon lots of little steps, but everything that we did here simply came from the canonical commutation relation, nothing else. And our very powerful operator identities that we've been working with. And now that concludes lecture 2 of module 7.